Welcome to Mrs. Lee's Chemistry Academy. Today we're going to focus on the continuation of intermolecular forces and the relationship between IMF and physical properties. Tying to the learning objectives from College Board, that the student is able to apply Coulomb's law qualitatively, including using representations to describe the interactions of ion and the attraction between ions and the solvent to explain the factors that contribute to the solubility of ionic compounds. That the student can explain observations regarding the solubility of ionic solids and molecules in water and other solvents on the basis of particle view that include intermolecular interactions and entropic effects. That the student can make claims or make predictions regarding relative magnitude of the forces acting within collections of interacting molecules based on the distribution of electrons within the molecule and the type of intermolecular forces through which the molecules interact. Now, the fourth type of intermolecular force is called Ion-Dipole attraction. It accounts for the solubility of ionic compounds in polar solvents. Now, when we have sodium chloride, when it's dissolved in water, it is ionic compound, so the ions will come apart, forming sodium ion and chloride ion. The positive sodium ion is surrounded by the negative end of water molecule, which is the oxygen atom. And the negative chloride ion is surrounded by the positive end of the water molecule, which are the hydrogen atoms, making sodium chloride soluble in water. We call that ion-dipole attractions. Here's a problem. Rank the relative strength of the ion-dipole attraction when strontium ion, calcium ion, and magnesium ions are placed in aqueous solution. Now notice their ionic radii, 113 picometer for strontium, 99 picometer for calcium ion, and 65 picometer for magnesium ion. The Coulombic attraction between ions and polar water is directly proportional to the charge of the ions, but inversely proportional to the size of the ions. Now notice all these three have the same charges, 2+. But magnesium 2+ ion is smaller than calcium ion, which in turn is smaller than strontium ion. Therefore, it makes sense that magnesium ion will have the greatest ion-dipole attraction, greater than that of calcium ion, and greater than that of strontium ion. Intermolecular force also determines properties of substances. Boiling point. The stronger the intermolecular force, the greater the amount of heat energy is required to overcome the intermolecular force to turn them into gas. So the higher is the boiling point. Second property, surface tension. It is the energy to increase surface area. Molecules at the surface area of liquid have higher potential energy than those in the interior. So liquids tend to minimize their surface area. Surface tension increases as intermolecular force increases. Third property, capillary action. The ability of a liquid to flow against gravity up a narrow tube. It results when the adhesive forces between molecules and the surface of the tube is greater than the cohesive forces between molecules. The fourth property, which is viscosity, resistance of a liquid to flow. It increases with increasing molar mass of hydrocarbons because molecules experience greater intermolecular force and are more strongly attracted to one another. For example, in our everyday life, we talk about syrup or honey being very viscous. Finally, vapor pressure. It is exerted by the vapor on the surface of a liquid in a closed container when the liquid is in equilibrium with the gas, at which the rate of evaporation is equal to the rate of condensation. Vapor pressure increases with temperature, but decreases with increasing strength of intermolecular force. So this is a very important point to note. Now, when water is placed in a sealed flask, the liquid molecules will begin to evaporate represented by the diagram. But when there are sufficient vapor molecules built up, then they will exert intermolecular force and become condensed into liquid again. So at a dynamic equilibrium, when the rate of evaporation is equal to the rate of condensation, then we define the pressure exerted by the vapor on the surface of the liquid as vapor pressure. Vapor pressure is dependent on temperature. At high temperature, more liquid molecules have sufficient kinetic energy to escape into the gas state. Therefore, vapor pressure increases with increasing temperature. Now you can see in this diagram we have fraction of molecule versus kinetic energy. The blue distribution curve represents that at lower temperature. Now the dotted line representing the activation energy or the minimum kinetic energy that the molecules must achieve to evaporate. And the painted blue section represents those molecules having that kinetic energy to evaporate. Now as we go to a higher temperature, the whole distribution curve will shift from the blue to the pink. And where the spread is wider, but now we have a greater portion of molecules having achieved sufficient kinetic energy to evaporate. So vapor pressure is dependent on temperature. Now, the normal point is defined as temperature at which the vapor pressure of a liquid is equal to atmospheric pressure, or 1 atm. Now here's a graph that's very useful in defining the boiling point of various liquids. When you go to the vapor pressure of 760 millimeter mercury, which is 1 atmospheric pressure, we can actually read the boiling point of the graph, 34.6 being diethyl ether, 78.3 being that of the ethanol boiling point, and 100 being that of water. A volatile liquid has weak intermolecular force and they produce high vapor pressure because the intermolecular force is weak and it can be easily overcome by thermal energy. The higher the vapor pressure of a liquid, the weaker its intermolecular force, the lower the boiling point. And here is the Clausius-Clapeyron equation that ties different variables together. If we know this set of vapor pressure and temperature, we can use it to calculate the molar enthalpy of vaporization of water and vice versa. Here's a linear graph showing natural log of P versus the inverse of temperature in per Kelvin. That produces a straight line with a downhill slope, and the slope is equal to negative enthalpy of vaporization over ideal gas constant R. And so if we can do an experiment to obtain data in terms of vapor pressure and temperature, then a graph can be plotted, and from the graph we can extrapolate 2 points being the x and y coordinates and plug it into the equation and calculate the enthalpy of vaporization being 43.4 in this particular experiment. And the percent error is 6.63% because the actual molar enthalpy of vaporization of water is 40.7 kilojoule per mole. Now here's another problem. Account for the relative boiling points of the molecules in the data table below. We have propane, dimethyl ether, and ethanol. They have similar molar masses, but the boiling points are very different. When we rationalize it, we look at propane being a nonpolar molecule with London dispersion forces, and therefore it makes sense that it would have the lowest boiling point, which is the weakest force. Now dimethyl ether is a polar molecule with dipole-dipole forces and LDF, therefore it would have a medium boiling point. And then with ethanol, which is a polar molecule with hydrogen bonding and LDF, and it makes sense that it would have the highest boiling point. The stronger the intermolecular force, the higher the boiling point, and the hydrogen bonding is stronger than dipole-dipole force, which is stronger than the LDF. Practice problem number 4. Here we're given information on the vapor pressure of 5 different substances. Rank them in increasing order of intermolecular force. Now these 5 substances are benzene, acetic acid, acetone, diethyl ether, and water. The higher the vapor pressure, the easier it is for the liquid molecules to break away, and the weaker is the intermolecular force. So the ranking is that the acetic acid being stronger than water, which in turn stronger than benzene, and stronger than the acetone, and then stronger than the diethyl ether. And here is a diagram showing their structures. Here's a table documenting the formula of each molecule, their molar mass, the kind of intermolecular forces they have, and whether the molecule is polar or nonpolar. When we look at diethyl ether compared with acetone, they both have same molar masses, but the carboxyl group in acetone forms a more electronegative end, creating stronger dipole-dipole forces in acetone than in diethyl ether. In the benzene, it is a nonpolar molecule with LDF. It has greater molar mass and delocalized pi electrons with a larger electron cloud. Therefore, its LDF is stronger than the dipole-dipole force of diethyl ether and acetone. That's something to be noted because generally speaking, we believe that dipole-dipole force is stronger than LDF, but in this case, it is not because due to the large size of electron cloud in benzene. And also, water has hydrogen bonding. It is a smaller molecule than acetic acid. Therefore, acetic acid would have an overall intermolecular force greater than water and exhibit the lowest vapor pressure. Remember, the stronger the intermolecular force, the lower the vapor pressure. Practice problem number 5. Account for the molar enthalpy of vaporization for the molecules in the water in the table below. Now we have water, propanol, and acetone, and the chemical formulas are given, and with the enthalpy of vaporization. Water has 2 sites for hydrogen bonding, so the intermolecular force is greater than the LDF and hydrogen bonding in propanol, therefore giving it a higher enthalpy of vaporization being 40.7. Now acetone is a polar molecule with dipole-dipole forces in LDF, but it's weaker than that of propanol because propanol has hydrogen bonding. So acetone would have the lowest molar enthalpy of vaporization being 29.1 kilojoule per mole. The stronger the IMF, the greater the amount of heat is needed to overcome the intermolecular force in order to vaporize the liquid into gas, and the larger is the magnitude of enthalpy of vaporization. Here's another question. Shouldn't he study the temperature changes caused by evaporation of several volatile liquids in order to relate them to the strength of intermolecular force? Now use the students' lab data to account for the relative strength of intermolecular forces. I believe that you might have done that in your lab where you would dip a piece of filter paper into the volatile liquid and then tied it to a temperature probe and then leave it at the end of the table and then observing the change in the temperature as the liquid evaporates. So here's a table documenting the formula, the molar mass, the intermolecular force, and a change in temperature. The rate of evaporation depends on the strength of intermolecular force. The greater the force, the longer it takes for a liquid to evaporate, and therefore the slower is the rate of evaporation and the smaller is the change in temperature, delta T. When you look at pentane and hexane, they're both nonpolar molecules with LDF, but hexane is a larger molecule with greater LDF. Therefore, hexane would evaporate slower with a delta T of 12 degrees C compared to pentane with a delta T of 16 degrees C. Now, when we look at butanol and ethanol, they are both alcohols, polar molecules with hydrogen bonding. But butanol is a larger molecule than ethanol, and therefore it has a smaller delta T of 1.7 degrees C. It would evaporate slower than that of ethanol with a delta T of 8.3 degrees C. So to sum it up, hydrogen bonding is stronger than LDF. The ranking by increasing intermolecular force and decreasing delta T would be butanol greater than ethanol, greater than hexane, greater than pentane. To sum up what we have learned today, students have learned formation and representation of the four types of intermolecular force: LDF, dipole-dipole, hydrogen bonding, and ion-dipole attraction based on molecular structures and polarity. That they predicted relative strength of intermolecular force from Coulombic interactions, and there's a relationship between relative strength of intermolecular force and trends of physical properties in molecules such as boiling point, molar enthalpy of vaporization, vapor pressure, and rate of evaporation. And finally, using the Clausius-Clapeyron Equation to calculate molar enthalpy of vaporization of water. From the team of MLCA, we'd like to thank you for watching our video, and we hope to see you again next time.